Math lied to us. Infinity isn't the biggest number. Well, it is, but there are infinities that are bigger than the normal infinity. Okay, before we get too far ahead of ourselves, let's slow down a minute. What even is infinity? Infinity is just the mathematical concept of endlessness. And this brings us to our first problem. You could count forever and still be just as far away from infinity as the day you started. You can count towards it, but you're never going to get there. Now, just to clear something up, in math, they use infinity as a mathematical object. So, not really a number, but kind of. You can count towards it, but never actually get there. And this is our first kind of infinity, countable infinity. The best example of this is the set of natural numbers. 1, 2, 3, 5,682, 16,439,209. You get the idea. Every positive number that isn't a fraction or a decimal is a natural number. Natural numbers are also called the counting numbers because they're the numbers that we use to count things. There's still some debate over if 0 should be considered a natural number, but 0 is actually really complicated and can totally be its own video. Anyway, natural numbers go on forever, but we can count them, so it's a countably infinite set of numbers. Even numbers is another countably infinite set. So is odd numbers, or all numbers that can be divided by 3 or 7 or 12,452. The Fibonacci sequence, prime numbers, all of these are examples of countably infinite sets, because we can match each number in that set with one of the counting numbers. Alright, let's get a little more complicated. Uncountable infinities are sets of numbers that can't actually be counted. The best example of this is the set of all real numbers. So this is all the natural numbers and 0 and the negative numbers as well as all of the fractions, decimals, and irrational numbers like pi or e. This is an uncountably infinite set because, well, where would you even start counting? But let's get even more infinite. Like I said earlier, all even numbers as well as all odd numbers and numbers divisible by 3 or 4 or so on are all also infinite sets. They're also sets that are contained within the set of real numbers. The set of real numbers also contains every other set that could be made with real numbers, infinite or otherwise. The set of all sets that a set can contain is called the power set. And because we have an infinite number of numbers, we can make an infinite number of infinite sets with the set of real numbers. So the power set of all real numbers is an infinite set of sets. Not all of them are infinite, but an infinite number of those sets are infinite. But we can keep going. We can make power sets of those infinite sets, basically adding more infinity each time. So from the first uncountable infinity, we can get a second, third, fourth, and so on. I think you see where this is going. The infinity of infinities. But there are infinities above uncountable infinities, exacting and ultra-exacting cardinals. These sets basically break infinity. There's a lot of really high-level math here, but basically what's going on is that exacting cardinals are sets that contain themselves as well as the sets that contain the sets that contain them. And I don't just mean they contain sets that are equivalent to the original set. I mean that they contain an exact copy of themselves and everything they contain, including the sets that contain them. And so, of course, a copy of that also contains a set that's a copy of itself and everything it contains, including the sets that it contains. And the copy of that copy has a full set of everything it contains, and the copy of the copy of the copy... Okay, you guys get the idea. It's like going down a never-ending hallway that contains infinite doors to anywhere in the universe, including a door that takes you to the hallway that contains infinite doors to anywhere in the universe. Except those doors don't just take you to those places are in the room that those doors open into. It's the fractal image of infinities. Or maybe it's more of an Ouroboros? Maybe both. Anyway, Ultra exacting cardinals are the same thing, but with the added bonus of containing mathematical rules of how to make themselves. So now that hallway has the code to replicate itself. And so that never ending self replicating hallway that has infinite rooms that contain everywhere in the universe also includes the never ending self replicating infinite hallway that has rooms that contain everywhere in the universe. These infinities get really complex and weird, so much so that the normal rules of math don't really apply to them. Well, maybe. See, above exacting and ultra exacting infinities are even bigger infinities where the rules are definitely broken. Normal math doesn't work, and the basic rules have gone completely out of the window. Below the exacting and ultra exacting infinities are the higher levels of uncountable infinities that still play by the rules. The problem here is that it's kind of unclear as to where exacting and ultra exacting infinities fit into this hierarchy of infinities. And it's actually super important to modern math that we figure out where they go, due to something called the hereditarily ordinal definable conjecture. Basically, this conjecture proposes that as you reach the upper limits of infinities, some of the rules start making sense again. That means that after a period of chaos where the rules don't really work, there's a region of infinities so big that things start to work again. So the main argument is if the rules get fixed when you go big enough, or if they stay broken, order or chaos. But there's another side to this argument. Maybe infinity doesn't even exist. There's a subset of mathematicians that subscribes to the finitist view of mathematics. The basic idea is that infinite objects, such as infinite sets, don't actually exist. While they do accept that all natural numbers exist, they don't think that the set of all natural numbers should exist as a mathematical object. Basically, trying to quantify infinity in any kind of way is meaningless because nothing is infinite. One quote I found that's kind of interesting is something that Doron Zielberger said. Infinity may or may not exist. God may or may not exist. But there's no need for either of them in mathematics. And honestly, he has a pretty good point. We don't really know if there is anything infinite in the universe. Some people believe that the universe itself is infinite, but in a recent video I talked about a paper that suggests that the universe isn't actually infinite. The universe does have a maximum size. We aren't there yet, but according to this paper, the universe can only get so big. That paper also says that the universe has a maximum age, or at least this iteration of the universe does. The universe might have a cyclical pattern of collapsing and being reborn in a new Big Bang, and who knows how long that's been going on. Anyway, the point here is that when we're using the existence of infinity as a foundation for math and physics, there's a chance that things are going to blow up if we ever prove that infinity doesn't exist. I mean, we already know that things can't get infinitely small. The Planck length is the smallest that something can be, and since it isn't zero, we know that the size of the universe, or at least of the observable universe, can be expressed in a finite integer. Anyway, back to the finitist movement. Over the years, it's been gaining more and more traction, and today it's looking more and more like they might have the right idea. They're pushing to form a stronger foundation in math by getting rid of the idea of infinity and setting a limit on how high numbers can go. Now, this would be a very huge number, like more than the number of atoms in the universe kind of huge, but putting an upper limit on things could help. One mathematician, Rohit Parikh, built a mathematical theory that was able to stay internally consistent when he kept things below this limit. This was pretty big because the current rules that we work under break down a bit when we get to those really big infinities, like we talked about earlier. But what would math and physics with no infinity look like? Well, there would be a lot of things that would have to be reworked. We've been using infinity for a really long time, so if we wanted to redefine everything without it, it would certainly be a lot of work. But it would have the potential to give us a more accurate and complete understanding of math and physics. There's an old parable that my mother used to tell me about a small church in a rural town. Every time they would hold mass, the cat would come in and meow and generally be a disturbance. To fix this, they started tying the cat to a pole that they had out front. Every time church was starting, they would first tie the cat to the pole. Now, eventually, that cat passed away and they got a new one to keep the grounds mouse free, but they kept up with the tradition. Every time they gathered, they started with tying the cat to the pole. Years went by and cats came and went, and they still followed the tradition, but they didn't need to. Only the first cat ever caused a disturbance, but they kept on tying the cat to the pole anyway. I think that Math's cat might be infinity. Someone came up with it a long time ago to explain something, and we just kept using it, but maybe Math has moved past it now. Maybe we don't need to tie that cat to that pole anymore. Many finitists think that infinity is actually holding us back, that dropping it and adopting new axioms would help us move math forward and deepen our understanding of the universe. Now, I am by no means a math expert, but I think they might be onto something. We don't know if our universe is infinite. It seems like it probably isn't based on recent studies. So, how did we end up basing so much math on something that hasn't really been proven? How would we even handle a huge paradigm shift like that? I'm not sure, but if you have any ideas, let me know in the comments. A big portion of this video was based on a video by New Scientists. If you want a more in-depth mathy explanation, go check out their video. Also, as I was writing this, Numberphile came out with a new video about Infinity too, so I'll link that as well. Anyway, make sure you like and subscribe, but most importantly, make sure that you stay curious.